describe okay. So we'll take a look at one very important concept in computer vision. So let me actually turn it off for a few minutes. Okay, so like we were discussing yesterday, right? In the end, we have some kind of classifier, and before that, we'll do some kind of a registration for the image. Okay, and then we'll classify whatever we want it to, right? And we grab the image and so on. So in the previous lecture, we took a look at what if the correspondences between the incoming image and whatever our reference image is, correspondence cannot be established via an active shape model. So if it's a phase, later on I'll go over a very famous paper called active shape model, where we can detect all the important points such as the location of the eyes, nose, chin, and so on. So in the incoming image, if we already have a reference image with location of these important feature points, then we can have the correspondences and then we can do easily the registration, right? So previous lecture, we looked at what if we cannot establish correspondences easily. So if we cannot establish correspondences between, let's say, incoming image and reference image. Okay, so then we can use the mutual information technique. So which was based on the joint PDF divided by the individual PDFs, and if we take the log of that and if we try to minimize this, whatever transformation we come up with that minimizes the mutual information. So if you recall, mutual information was something like this, log of let's say
pair, right?
P of A, B,
Yep.
right? The joint PDF over P of A, P of B. Okay, A and B are the intensity levels. They vary from 0 to 255, right? So A equal to 0 to 255, B equal to 0 to 255. Okay, and I think there was something, a scaling factor over here, the width and the height of the image. So basically we can set this as a loss function or cost function or error function, however you want to think of it. And so if we have one image, so this could be the incoming image as an example, right? We have a reference image, let's say I2 is our reference. So in our previous lecture, the idea was, let's apply a transformation with A, B, C, D, T1, T2, or just A, B, T1, T2 if we assume there's no shear. Then, so the idea was this cost function, so as we apply it to transformation to I1 and compare it with I2. And so then we compute the mutual information with transformed I1 and I2. So if it produces a low value, then that transformation is the one that is registering the two images, right? Okay, so how do we know which way to move these parameters over here so that the cost keeps getting lower? You guys remember or no? how would you, so in the beginning we'll assume randomly, right? A might be 0.1, B may be 0.2, this may be 10, this may be 12. So there's a random initialization of these. Correct?
Is that amoeba?
Yeah, the amoeba algorithm, very good. So amoeba algorithm, if you recall, if we have 4 unknown parameters that we need to optimize, so how many nodes will we create in the amoeba?
N+1.
N+1, which is 5. 5 nodes. Each one of them will have A, B, T1, T2, randomly initialized. A, B, T1, T2. Randomly initialized, right? So then we compute, if we apply this, one of these nodes, A, B, T1, T2, we apply to the incoming image. And we compute the mutual information with the reference image. Then out of these 5, we will have the best, right? One of them will be better, will produce lower mutual information cost. We put a negative over here so that the lower, from an optimization point of view, if we try to minimize the, because we want to maximize the mutual information, but the loss will be the negative of the mutual information because we always try to reduce the loss, right? So anyway, one of these, if you recall, will be the best, one of these might be the worst. Then, as you saw, based on the worst, we will do a reflection, we'll do a double reflection to see does that improve the cost or not. So essentially these 5 particles keep moving until, you know, we cannot reduce this anymore. So that was the idea behind mutual information and using the amoeba or the Nelder-Mead algorithm to come up with how do we register an incoming image with a reference image where the corners or salient points cannot be determined that easily, right? So in deep learning world, hopefully in a couple of lectures I'll show you how mutual information is extremely important. So 2 things if you can remember from this one. One is given 2 images. So especially mutual information is a very popular cost function when 2 images are involved. Okay? So it tells us the essentially the similarity between the 2 images, right? In deep learning, so this was one application. In deep learning, as I mentioned, we have an input image, especially if we are creating, let's say, autoencoders, or even if we're not creating autoencoders, we are creating deep CNNs. How do we know the parameters that we picked in the CNN are as good as they can be? So as I mentioned to you, we, not in the classifier stage, before the classifier stage, we do a deconvolution. So we do basically a reconstruction via deconvolution. Okay, in the next deep learning lecture, I'll go over the deconvolution, so that I can show you exactly how that's done. But anyway, so then once we reconstruct, what we can do is we can compare it with this one, how good of a job CNN is doing, because from, remember the purpose of the CNN is basically to learn features, right? The first layer learns very low-level features like curves, and then gradually the second layer will start to put together like shapes like eye and so on. And towards the end, it will try to put together sort of like a face. So one of my PhD students and I, we came up with the concept that, let's use mutual information as a mechanism to guide the CNN towards as good of a job as it can do. So anyway, so this is what I'd like you to remember, that this is how we compute similarity between two images, right? Okay, so now today let me show you another very, very important concept. And if we had more time, I could give you an assignment on it, but I know you guys are already behind, so at least if you guys can learn. Okay, so let me see if this one works better. Okay, so let's say we created some classifier. Okay, and suppose the classifier is not doing a good job. Okay, somebody else says, oh, you know, rather than using a particular design of a classifier, you know, we should try something different. So we pick another classifier. Okay, let's pretend this is 70% accurate. This is 65% accurate, right? And let's say classifier N is again maybe 75% accurate, right? So we had different techniques for identifying or recognizing an object, okay? Each one of them, so this could be one kind of neural network, this could be some other neural network, another technique could be a PCA as an example, right? So let's pretend none of them do that great of a job, okay? If you had to pick one, how would you pick one? You have some
highest, of course.
Highest, of course, right?
I mean,
But so here's the interesting part about today's lecture, is can we combine these in a certain way so that we are getting more than 99% accuracy? Okay.
Yes.
Of course, I won't be asking that if the answer is not yes, right? Okay, so the question is how? It doesn't seem right? Okay, so the example would be something like this, okay? Let's say there's World Cup soccer or, you know, Super Bowl in football, okay, so whatever game is coming up. Okay, so you see on TV, all the experts come in and they say which team will win, right?
Sure.
Okay, so one expert says, let's say team 1 will win, for whatever logic, right? Another, so this is expert 1, expert 2 says, oh no, team 2, expert N, again team 1 or team 2. So all of them have their opinion, right? Okay, if you were to go by, because they know the game better than us, then if you were to go by which team will win, how would you decide that?
You wait them.
Count as a frequency of what? Like team here is
I mean, one possibility would be if it's a binary decision, right? In the end, if let's say there were 12 experts, okay, if 5 of them said team 1, 7 of them said team 2, what would you do?
Team 2.
Team 2. Okay, so that's an easy concept. That concept is called bagging. Okay, so bagging is simple averaging. Okay, that, I mean, works to some extent, but it's not going to give us really highly accurate answer, right? Okay, so there's another concept that I'll describe to you today, which is called boosting. Okay, so so it will not work in this case, otherwise, you know, you can start betting money and start. But in certain cases, it's a beautiful concept, okay? So again, as you guys have seen, you know, throughout deep learning, some of you who took parallel computing, what was our main theme in all of these courses, right? whatever we are doing, essentially we are trying to optimize something, okay? For example, neural networks, what are we trying to do? Optimize what?
Loss function.
Loss function, right? So depending on different situations, we come up with different loss functions. In parallel computing, for example, we looked at many different, like genetic algorithms, in-colony optimization, swarm intelligence. Now you guys also saw in this course, for example, the amoeba algorithm, right? So very similarly, boosting is, think of it, another kind of optimization problem. The optimization in this case is given a set of weak classifiers. Okay, by weak, what we mean is slightly better than 50%. So these experts are pretty, they're not like, like when people are on television, when really great experts come in and perhaps they have more insight into, or more accuracy. But let's pretend we have a set of classifiers, each one of them, and rather than doing even 70% is too high. Let's pretend this is only 55% accurate. This is only 52% accurate, as long as it's more than half. So the beauty of the boosting approach is we can combine these many, many weak classifiers into an extremely strong classifier such that we can get almost 99% accuracy, okay? So how? There's a theory behind it. So in the end, as you will see, we'll come up with a cost function. How do we optimize the cost function after we have initialized it? Of course, anytime we want to minimize something, we take the derivative, set it equal to 0, so that whatever parameters we are looking for get enhanced as much as possible, right? Or give us a final answer as good as possible. So let's take a look. Okay, so to save time, I'll go over, I've already put it on the website, a very, in my opinion, easy to follow article, for the most part. Okay. Still, first time when people read it, they get confused. So to further clarify, I have created a simple example to clarify it further. Okay, so anyway. Okay, so on the website towards the bottom, you will see it's called AdaBoost tutorial, AdaBoost example. Okay, so if I go to the, so this is a very popular tutorial on adaptive boosting. So as you can see, AdaBoost and the Super Bowl of classifiers. So anyway, this person did, in my opinion, a really, really good job in explaining it. Still, the math becomes, sometimes confusing, but hopefully we'll be able to clarify. Okay, so again, the author over here is saying, let's say we have 11 experts, as an example, to predict who will win the Super Bowl, right? So this K1 of X of I, K2 of X of I, so this is their decision, okay? So if team 1 will win, they will output 1. If team 2 will win, can you guess?
0.
No. -1, okay, in this algorithm, okay? Because that's how the equations are set up, as you will see. So once again, 1 or -1, as you can read it later, is the answer from this each expert. So X of I is the input. So when we are creating, for example, classifiers, remember we feed in, so this is a classifier. So forget Super Bowl for a second. We may feed in x1, output may be 1. We may feed in x2, output may be -1, meaning this belongs to the second class, this belongs to the first class, right? So same way, x3 may be 1 or -1, okay? So again, the idea is, how can we combine these, in this particular case, 11 expert, doesn't have to be 11, could be 5, could be 20, could be 200, okay? How do we combine the decision of each one of these experts such that our final classifier is as accurate as possible, right? Okay, so alpha 1 is basically a coefficient. So for example, could be, let's say, 0.2, 0.31, and -0.11, something like this, right? Actually, sorry, I think it will always be positive. Okay, so anyway, so basically everybody's decision, as you can see, is weighted, so that finally all we are doing is getting a weighted average, okay? In the example that I gave you, let's say there's a Super Bowl, 7 experts say team 1 will win, 5 experts say team 2 will win, right? So remember, we did basically an average. So if there were 12 experts, you can see, in order to understand this equation, if we were not using adaptive boosting, what will be the weight of each one of those 12 experts? What's that? Equal. So there will be a number, right?
Yeah, 1, 0 or -1.
No.
So which is what?
No.
1/12.
1 over 12, exactly. Okay. So each one is 1 over 12, 1 over 12, because they have equal weight, right? Now let's pretend out of these 12 experts, somebody has done great predictions in the past, knows the game better than anybody else. Then intuitively, would you give that classifier or that expert same weight or more weight?
You give them
More weight, right? So essentially we want to develop a theory so that based on how on the training data a particular classifier operates, then the weight should come accordingly. So we want to develop a full mathematical theory rather than simply saying, oh yeah, this expert is better than this one, give it double the weight. Okay, so
these weights would be initialized randomly, Professor?
you'll see the whole theory. The weights are actually, in the beginning there's no weight, but once we go through the math, you will see how it will come out, right? Okay, so that's the idea. So once again, K1 is the classifier, will produce 1 or -1. Alpha is basically the coefficient, like a number, like 0.2, 0.1, 0.7, right? Okay, so the final, so let's say we have 11 classifier. Each one is giving us 1 or -1. And let's pretend we already, through some previous knowledge, already have given these some weights, okay? So my question to you guys is, in the end, what will this do if I go through all of them? Let's say first classifier said output should be 1. Second classifier says output should be -1, and so on, for a given input. So suppose we fed in x5. So how would you know that the answer over here is predicting positive outcome or negative outcome?
Wouldn't the answer be?
I mean, it's a summation of either all negative numbers if they're all choosing one thing, or all positive numbers. So
Okay.
I think
So in this, yeah, very good. So in this particular algorithm, if it comes greater than 0.5, the sum of all of these, then it is
Favor,
positive.
yes.
If it's less than less than 0.5. If it's less than 0.5, then
What, 0.5?
what was that question?
Why is it 0.5 instead of?
Again, as you go through the math, hopefully it will become clear. Okay.
Some of that weights must be 1, right?
Oh, sorry.
Yeah,
Sorry, it's 1, not.
Would it be between -1 and 1, the sum of all of them?
Where did it go? I've written it somewhere over here.
I mean, there would be, if they all equal 1 or -1, there's
Yeah.
no way you could reach.
Okay, so
0.5.
sorry, in this particular development, okay, there is another development where we use 0.5. In this particular development, the sign of the weighted sum, so basically if this is greater than 0, then it will be the positive class. If it is less than 0, it will be the other class.
Yep.
Okay, so anyway, let's go through. Okay, so basically the way this algorithm starts is, okay, so we first of all decide on number of classifiers. Okay. In some cases, we decide in advance. Some cases, as we keep going, we say, okay, let's add one more classifier. Okay. Once I give you a concrete example, this will become clear. But anyway, in this example, again, let's assume we wanted to create, 10 or 11 classifiers total. We wanted to combine them such that final decision is better than individual ones, right? Okay, and so in this terminology, capital L over here is basically number of classifiers. Okay, so this could be 10 or 11 or 200 or whatever, right? And as you can see, what are these? This is our training data. For example, this could be 1,000 as an example. If we have 1,000, where we already know what is the expected output, okay? So this is called the scouting table, right? If you take a look at the scouting table over here, in this particular mathematical development, again, there are slight variations of this idea, but in this particular article, what the author assumes is if the decision is correct, meaning the classifier 1, based on input of x1, produced whatever the correct class was. Okay, if it was correct, then we'll put a 0 over there. If it was incorrect, then we will put a 1 over there, right? So as you can see, if we take a look at the first column over here, okay, let's pretend all of these are 1s, meaning there's a 1 over here, 1 over here, everything is a 1. The 0, 0 appears here, here, and here. So what does that mean out of, if let's say n is 100? So this is 100. So which samples are being correctly predicted by the first classifier? 3, right? x1, x2, and x100, right? Okay. Very similarly, if you take a look at the classifier 2, which one is it predicting correctly?
X1,
X2 and X.
Oh, sorry, correctly, X2, Xn.
X2, and let's pretend again these were all 1s, x2 and
XN.
and so on, right? Okay, here this is predicting. So in the beginning, in this adaptive boosting algorithm, the very first, if we wanted to pick total 10 classifiers, right? Remember our goal is what should be, we're not designing the classifiers, we are combining the classifiers. So what should be the weight of each one of those 10 classifiers as an example, right? Okay, so what we do is we first pick one classifier. Okay, so which one will we pick out of this table?
First one.
The one that produces the highest error or one that produces the lowest error?
Lowest error we should pick, right?
Lowest error, right? Meaning which has more ones or less ones?
So these,
Less ones.
Less one. So we'll basically go to each column, see whichever classifier, let's pretend classifier number 7, if we add them up, has the
Least amount of.
lowest number.
Or we can calculate the probability also, right? Of one.
There's no need for a probability, it's a simple counting over here, right? So if this sum of this column came out to be the lowest of all, then classifier 7 will be our very first classifier that will pick.
Highest.
Okay. So anyway, so this part is pretty straightforward. Now let's go to the math development. Okay, so let's take a look over here. See if we can understand this equation over here. Okay, if you take a look at M is our iteration in adaptive boosting. Okay, meaning how many classifiers have we picked correctly so far? Or have we picked, not correctly, have been selected and weights assigned to them. And alpha was the coefficient, so maybe I should say, because there's weight as another terminology, another meaning over here, so and coefficients assigned. Okay, so to understand it easily, let's pretend M is 6 right now. Okay, so as you can see, we have come up with C5 of x of I. So this will be alpha 1, K1 of x of I, plus alpha 2, K2 of x of I, and it will go up to K5 of x of I, and alpha 5. Right? And so, in this equation, what we are assuming is, let's pretend somehow we already know what alpha 1 is, meaning it could be 0.15, 0.2, 0.3, whatever, right? So we already know the coefficients of the 5 classifiers, okay? Now our goal is to pick the 6th classifier and find out what should be the weight of it. So once again, we're not designing the classifiers, the classifiers have already been designed. Our goal is to decide what should be the weight of each one of those classifiers, right? Whether it should be 0.1 or 0.3, the coefficient, I shouldn't say the weight. So in this case, we are assuming up to M. We already know what are the coefficients of the classifier. Now we wanted to add one more classifier, right? So let's take a look at the next equation. Does this seem right?